In this video, we're going to take a look at electric current, which is different than electric potential. This is probably the most challenging concept in this unit as we talk about electricity and magnetism, is separating the difference between the two. So electric potential is what charges bring to the table, and then current is the actual physical charges themselves. And rather than talking about discrete particles like discrete electrons or discrete electron holes, if we're talking about conventional current flow, we want to think about instead more like a fluid. And so we want to anticipate the rate of charge flow through a conductor, and that's what current really is. The SI unit for charge is coulombs, and the SI unit for time is seconds, of course. So we define 1 ampere as 1 coulomb per second. When we provide a path for charges that have electric potential to flow, we can harvest their potential energy and do useful work. Might be lighting a light bulb, might be spinning a motor, but we have to provide a complete path. So in this situation, we can see that only one of the pictures shows a complete path from the positive side of our battery, or sometimes referred to as an electromotive force, an EMF. And then that path has to go through our device and then wind up on the negative side. So only option C is actually a way to light a light bulb. As I mentioned in previous video, we're kind of stuck with this electron flow as opposed to conventional current. So this negative end of our battery, which we call an anode, which is essentially an up path for charges to flow, and then the cathode, which would be the down path for electron flow. But at some point, and mostly it's attributed to Benjamin Franklin, started representing current flow as being from positive to negative. And he had and this refers to some work that he did with electrostatics and some writing that he did. Regardless, the rate at which current flow is going to be proportional to potential difference or voltage. And if you remove that proportionality symbol, you can replace it with an equal sign by using something called resistance. So we'll go out and take a look at a simulation involving resistance. So this is a really simple simulation, but it does get to the heart of what's happening inside our device. So here's our device right here. That could be a good conductor, might be a bad conductor. It all depends on what its resistance is. And so we have a voltage set up here, 1.5, 1.5, for a total of 4.5 volts altogether. And then the current is milliamps, so that's 0.009 amps. And as we increase the voltage, we can see that there's more current flow. But where's the resistance coming from? And it has to do with the fact that our material, whether it's the filament in a light bulb or the wire in a motor, is going to have energy sharing collisions with electrons as they go through this material. And the density with which those energy sharing collisions happen has an impact on resistance. Let's imagine the water analogy works really well here. So let's imagine the current through a river. And if the river is a nice deep channel without a lot of rocks, and there's very low resistance and the current is swift. But then if we get to a place where there are a lot of weeds or a lot of gravel, then the resistance actually increases. So as I increase resistance, you can see the number of impurities decreases. So that's a pretty straightforward relationship. It's a linear function, and this is called Ohm's law. Now, we're probably going to want to take a deeper dive into what makes up resistance. So I'm going to share my screen again, and we'll go back to our notes. If we're plotting voltage versus current, then we can see we should get a straight line if it's truly linear. But some materials don't offer up this linear behavior. Materials that do are called ohmic, and materials that don't are called non-ohmic. So we might see resistors that show up like this. A resistor is just a device that's used to control current flow. If we have a battery and we just connect the positive side and the negative side together, we'll probably have some very exciting results, just like if you unbend a paperclip and insert the two ends into the two sides of an electrical outlet. And it'll be very exciting for a short moment of time, but yeah, that is actually what we call a short. So if we increase the resistance, a short would be almost no resistance. If we increase the resistance, we can throttle back that current. And so this is some evidence of a color code, which is not essential for use in our course. So what are the factors that affect resistance, though? So this is an important relationship. This indicates that if we have a conducting material, that the longer the material is, the more energy sharing collisions are going to happen, and the resistance goes up. And the cross-sectional area, if we have a wider cross-sectional area, then there are more pathways for charges to find. And so that's going to lower the resistance. And then, of course, the resistivity depends on what the material is. So if I was thinking about a traffic jam, if I had a long way to go in the traffic jam, it's a lot of resistance. But if I was to open more lanes on the traffic jam, then that's going to lower the resistance. So that's a nice, easy way to think about that. Now, here we see resistivities. You can see that for our metals, the resistivities are really low. Silver is the best. Copper's close second, and of course, copper is much less expensive than silver. So that's why we see it used quite a bit. And then we have this weird zone of semiconductors, and finally insulators. So that's a big difference. That's 20 powers of 10 different in resistivity. We also see this temperature coefficient happening. And so this indicates that the resistivity is going to change a little bit depending on temperature. And we'll have a video that talks about some problem solving that goes along with this. So we start off with some base temperature, like room temperature, 20 degrees C. Then any temperature higher than that, like imagine a glowing light bulb, that's going to be pretty hot inside. And the resistivity is going to increase. So resistance increases with temperature for most materials, but sometimes semiconductors act a little bit different. Okay, and then we'll talk about power shortly. All right, great. Let's take a look at our circuit construction kit again, and we saw that we can actually measure current and we can measure voltage. So I can put a voltmeter in here. And I can put an ammeter in here, but this is an important distinction. How do you measure current? So voltage, voltmeter is measuring the potential difference between 2 points in our circuit. We have the plus side over here and the negative side over here. So we're measuring a difference. A voltmeter has a lot of resistance. So very little current actually goes through that. But with our ammeter, we actually want all the current to go through there. So what we're going to have to do is we're going to have to create a break in the line. And then we can install the ammeter. There we go. And now I'm measuring the current. So the current is 4.4 amps, and I've got 44 volts. So I have a pretty good idea about what the resistance is going to be. Yeah, it's 10 ohms. And if I crank up the resistance, you can see the current falls off quickly. In our pivot lab, what we're going to see is a setup. We'll see a video that looks like this, and we're going to have both the voltmeter and an ammeter. And what we're going to see as I play this video, we'll see we have a power supply here, and our lab assistant is going to increase the voltage and look at a corresponding increase in current flow. Notice that just like what we did before, the voltmeter is connected between the two ends of the resistor, so it can measure the potential on the way in and on the way out. But the ammeter had to be connected as part of the path. So we'll have more words about this later on, but this is called a series connection, and this is called parallel. Okay, well, that's a good start to understanding Ohm's law. And I just realized I forgot to share my screen again. Right, so here's what our pivot interactive is going to look like. And we're simply going to see a voltage increase as our lab assistant turns up the power supply. We see an increase in voltage and a corresponding increase in current. So this is the lab that we're doing for this week. And that'll be posted tomorrow. All right, sorry I forgot to share my screen there, but this is a good start to understanding how Ohm's law